We will learn how diffusion LLMs predict tokens, how they generate tokens, how they calculate tokens. We will learn how to code it from scratch. You will understand and be able to write this prediction code by the end of the video. No matter how difficult it seems, you will understand this. Link to GitHub below. So let me give you a summary. So let's say we have a prompt, the temperature and weather in, and then there is continuation to the sentence. And in diffusion models, we just mask every token. We put this mask token instead of the tokens that we need to predict. And now we're gonna try to guess these tokens multiple times. So in the first iteration, we will just guess each token here, put some words. And then we will keep some of the words according to the rules. I'll explain the rules. And then other words we will again replace with mask. And then we will then refine those other words again. So we will iteratively, in each iteration, we will predict all of the words and then keep most likely ones, and others that are not so likely, we will just predict again for maybe some number of iterations. So how do we guess them? So we have a vocabulary of tokens, let's say 200,000 possible tokens, words, everything. So for each of these, just like in autoregressive transformers, based on the context, we will calculate probability for each word in the vocabulary to be this word here, this token. So let me repeat. For each of the tokens, we will calculate probability distribution over entire vocabulary. Each token in the vocabulary will get a probability of how likely it is to be this here. And then for this, all of the tokens will get different probabilities, etc. We will talk more about this in the video, so just bear with me, even if it's tough to understand right now. So once we have probability distribution for each of the tokens, we will take it and we will add some randomize it a little bit, not too much. We will randomize it a little bit, so we will mess it up a little bit. And then we will just pick the highest likely token, most probable token with highest probability. So we are randomizing it to do some exploration and add a random element to this diffusion model, not to make it so deterministic. So this messed up probability distribution will make it a bit more random, so it's associated with creativity. Then we will pick, in this code, we will pick just the highest probability token. And remember, because we messed up the probabilities, the highest probability token is a bit now random. It's not really what the LLM calculated. Now it's a bit more random. So after we replace each of these tokens, mask tokens, with some token, we will then calculate C, the real probability, before we messed it up for these tokens. So the real probability. And we will just keep tokens that have high real probability. And we will replace, let's say, so this one, let's say this should be in and this should be tomorrow. Let's say these have high real probabilities and these have lower real probabilities. So again, when I say real probabilities, this is what LLM calculated probabilities before we messed up probabilities to make it more random. So if this is tough, it doesn't matter. I'm just summarizing now. We will go step by step later. So then we just repeat the process. We let LLM calculate probabilities and then mess it up again to make it more random, and then pick according to those messed up probabilities, and then see what are their LLM calculated real probabilities, and just keep the most likely tokens and mask others. So, and then let's say this token will be replaced as well, whatever it is, I don't know. And this one as well. And then in the end, we just do the same and pick the last token. And that's how it works. So I know it might be confusing a little bit. So I will show you everything step by step. We will start from the beginning to the end and understand all of this and understand the code. In GitHub, we just have these two main files, LLaDA generate and LLaDA wrapper. Let's take a look at LLaDA generate first. So it loads a pre-trained LLaDA model, this one, converts a user question into tokens, iteratively generates an answer using masked token refinement instead of traditional left to right autoregressive decoding, decodes and prints the answer. Generate function, this is the core loop implementing non-autoregressive generation using a diffusion style iterative denoising. It takes model, the LLaDA model, a masked token predictor. What? Maybe this class model. Okay, we'll see later. Okay, prompt, tensor of input token IDs from the dictionary, steps, number of refinement steps per block. So in LLaDA, refinement steps refer to the iterative updates of a masked sequence of tokens during generation. So there are iterative updates to the masked tokens. How many? I guess it's not the same for every token. Let's see. Instead of generating one by one like GPT, it generates all tokens at once and refines them over time in several steps. So it refines after generating all at once. Let's say you want to generate the sentence, the cat sat on a mat. Step 1, initialization. It's all masks. A masked sequence starts blank. Step 1, the model fills in a guess. The dog sat on a log. Okay. It might be incorrect or low quality, maybe. But how good is this guess? I think the guess is still good. Step 2, model sees its own previous prediction, then refines it. The cat sat on the mat. So I guess it changes this word maybe a few times until it gets to cat. So it looks at the full sentence, including prefix prompt, which was not shown here, I guess. Predicts better tokens for masked parts, replaces low confidence or wrong ones. This is like denoising the sentence over time, starting from a rough guess, improving it step by step, yeah. Each iteration of the outer and inner loops in generate is a refinement step that is progressively improving the masked sequence. This is your denoising process. So, step, predicting the probability distribution for masked tokens. This happens in this line. Logits is equal to model x.logits. Oof. Let's break this down. What is x? X is the current partially masked sequence of token IDs. Example, Lily can run 12, mask, 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 okay. X includes the original prompt, fixed, plus masked. Original prompt and masked tokens. What is logits? After passing x through the model, we get these logits. You get logits shape is going to be batch size, sequence length, number of tokens, and vocab size. Oh, okay. For each token, we get a probability distribution over entire vocabulary, showing which word in the vocabulary is most likely for this token, for this place. But why sequence length? Is it just this sequence or this entire sequence? I think it should be just this sequence. So let's see here, logit. So this is the batch size. I think we'll see later. So number of sequences and position in the sequence. And for example, position 4 in the sequence will have entire probability distribution over the vocab, over the whole vocab, but this is not probability distribution as you can see. It doesn't add up to 1. So it's just still logits. And later, I guess we take softmax to turn it into probability distribution. Yeah, we just take softmax of it over the last dimension, inner dimension, so over this dimension. No, I mean, I don't know. Yeah, over this dimension, I guess. I don't know. What is the last dimension should be like this whole thing. So there is one more dimension. Yeah. There is one more. Logits has 3 dimensions. And if you show these 2, you get this third. So we take softmax over the vocabulary dimension for each token position. So then for each of the positions, we just sample based on the probability distribution to pick the highest likely token, most likely token. But we don't actually pick from the original probability distribution. We actually want to add some noise, some randomness to it. Because in sampling, especially in early stages of denoising, we want to encourage exploration. So we want the AI to try different tokens. So we will mess up the probability distribution a bit, add some noise. So it's in this line, add Gumbel noise and pass in Logits and temperature. And higher temperature will mess up noise more. That's how temperature works usually. I'm guessing it works here as well. So that's how we get randomness when sampling, when denoising, when trying to find out which is the best token. Let's break it down. X0 is shape, batch size, and sequence length. Gives predicted token ID at each position. Okay? It's just a list of predicted tokens. And then torch unsqueeze. So we need to calculate this confidence. This comes after picking the argmax, our random noise, at our random token in X0. Now we have sequence of these tokens. So after it picks probabilities, it will again take softmax of the original Logits and use it for some reason. So you know that we picked tokens from this noised probability distribution, but we still want to know how confident the model was originally to pick for these specific tokens. Because without the noising, how it was actually confident, what was the actual probability. So that's why we pick those original Logits again, the probability, yeah. We use this confidence to decide whether to keep or remask the token in future steps and remask it and guess it again. Now let's go step by step and build a mental model carefully. Assume you are at one denoising step in generate. So you already did one denoising. So you get these Logits by running the model. So to repeat, this will output raw scores for each token position and vocabulary word in the vocabulary. So each position gets all of the scores in the vocabulary. So shape is batch size, sequence length, vocab size. These are not probabilities. Then we add noise to increase randomness. So we don't get the same thing always. Now we have noisy version. Now we pick the highest argmax of that token for each position. But wait, how confident was the model about this choice? Just picking it doesn't tell you that. So we will compute the same softmax again and not add Gumbel noise to see how the real probability of each token that we picked. So let's explain this line of code. So originally, so now we have x0. Before this line we have x0 that has batch size and sequence length, which it has all of the picked out tokens. And what we want to do is to the each picked out token, which is this batch size and the sequence number, we want to add probability for that picked out token as well. So what that will do is, you can see that we want to add this new dimension. So we will just use unsqueeze. So if we have x0 at shape, batch size and sequence length, we will unsqueeze the last dimension and we will get now number. So one dimension here as well for each of the tokens. It will have one dimension vector or number inside. And we will put the number, the probability that corresponds into that new dimension. Then we will use this torch.gather, passing p and then specify the last dimension. So remember that p has shape, batch, sequence length, and vocabulary. So for each sequence position entire distribution over vocabulary, and this index has shape batch, sequence length, and 1. So let's understand how this gather works. So P has position B, I, vocab size. So dimension -1 means gather along the vocab axis, which is -1, which is the last axis, for each position, which is going to be the prior to axis, which is batch size and sequence length. And PyTorch implicitly indexes all other dimensions, batch size index, using broadcasting. Let's break it down. So this P has batch size, sequence length, and vocab, okay? And then X0 has batch size and sequence length. These are predicted indices. And then index, which vocab ID to look up for each batch size and sequence length. So that's going to be same vocab ID that's written here. But here we also have some other number inside this L, another dimension inside of this L. Let's see what torch.gather does. So input the source tensor. Let's say it has shape, batch size, sequence length, vocabulary size. And then dimension is the dimension along which to index. What that means, we'll see. And then index, a tensor of indices that tells what values to extract from input. So it looks at index tensor and uses those indices to pick values from input tensor along the specified dimension. So you have input tensor, you say which indices to pick, 1, 2, 3, 4, and then say over which dimension. If it's -1, it's going to be the last innermost dimension. Let's say our input tensor is this one, and our torch tensor, our indices are 2, 1, 0, 0, 2, 1. So if we want to gather over dimension 1, which is going to be this innermost dimension, let's see, first number 2, so it's going to be this one, then number 1, then 0. So 30, 20, 10, okay, 30, 20, 10. And then 0 to 1, so 0 to 1, 40, 60, 50. So that's going to be our new tensor. So you know that our x0, this sequence length, it just contains indices of each token in the vocabulary. So we can use those indices to pick the probability distribution corresponding to that token. And that probability distribution is saved in this P tensor. So that's all of the... So we just take the number index in this L and pick the whatever that index picks in this V. If it's 3, you pick the third probability in this V. So we need to reshape this x0 because this L, it's an array of vectors, of numbers. But we need to put each number to a separate dimension. So then we will in gather, we will go just those dimensions. Like we will just take that last dimension that has just one number and then pick from this other probability distribution. So you see here, we are just, so index is going to be torch unsqueeze x0 and then put each number in the token sequence into a single, like a separate, like just put it into one dimension for each number because we unsqueeze the last dimension. So we also need to squeeze the last dimension after because the result of gather has BL1 shape. So each of the token probabilities is now in a separate bracket, separate dimension. So we just want to put it into one long sequence, those probabilities. So we want to unsqueeze and put it into one vector. So here, you see how we got after our gather, we got this torch squeeze over the last dimension. And that's going to be our x0p. It's going to be batch size, sequence length, and each sequence number has just probability for the corresponding picked token. So if you don't understand, you can either ask ChatGPT, you can get this code, you can copy this part of the code, but we can also check the code. So this is example. Let's say we got probability distribution for first position. We get all of this over vocabulary. And then this is entire for second position probabilities over whole vocabulary. So this is token 1, token 2, token 3. And then let's say they predict these tokens. So they predict 0.7, this one, and 0.5. So now we need to create a new tensor with 0.7, 0.5, like this. So after this finishes, we will get 0.7, 0.5 as x0 probabilities. So x0 tokens and x0 probabilities. But all of this is only if we choose this low confidence remasking. Later we will keep high confidence tokens that show high confidence score, and then we will just remask and generate again low confidence tokens, low score, low probability tokens. We also have this random where we don't actually just, where we don't do this gathering, we just do this random operation. So we will randomly choose which tokens to mask again and to predict again, as opposed to getting their probabilities and checking them. So this remasking random, this just assigns random confidence scores to every token position. So we will, this is useful as a baseline or to introduce exploration during training, but not as effective at the generation time as low confidence. Then we have this line, XP, and then choosing some index, which is taking the whole batch and then choosing some probabilities and putting them to minus infinity. So let's see which and how and what. So now that we have confidence scores x0p, we do the following steps. So this prompt shape 1 is the sequence length, number of tokens. I guess shape 0 would be the batch size. So shape 1 is the sequence length, number of tokens. Let's assume it's 20. So those tokens don't need to be masked. Then we have this plus number of blocks plus 1 times block length. And this column. So that's the beginning. So we take from this column means to the end. So we need to find which index here we start from, and we take everything to the end. And then we take that for each batch. So what is this index? So it's the beginning. So we skip the beginning prompt, and then block length. Let's say block length is 32 tokens. And if this is the first block, so we are doing diffusion in blocks, you know, we first do one block and then predict tokens in the next block. So not all at once. So if this is the first block, number index 0, then we start from index 20, which is the prompt length. If this is the second block, which with index 1, then we start from index 52. So now we start from this index. So the current decoding block is positioned at 20, 52, including 20. What is this? This is kind of weird. You can ignore this sentence. What is this? So this is what I was talking about. We take all batch sizes and then this number 52 and to the end. And we set all of that to minus infinity. So we should know that we have the fixed prompt in the beginning and then blocks. So we don't denoise all at once, but we denoise block by block. We loop through one block at a time and do steps of refinement just for that block. So this line is masking all of the positions after the current block, setting them to -infinity. So we don't update those positions at all, just the current block. But what about previous blocks? We will mask previous blocks a bit later in here, in this confidence line. So this little line, torch where, we have mask index, so a tensor that's showing all of the positions for the mask tokens. We give it the probabilities, and we give it this argument. So this is tensor, and this argument -infinity. So what this will do is, if token is not masked, so if the index is not contained in this mask index vector, then it will set it to -infinity, to this, inside of this probabilities vector. So all of the not masked will set to -infinity. And you see that it will create a new tensor, and the new tensor will be batch size and sequence length. So everything that's not indexed will be -infinity, and everything that is indexed, so if x bi, so if it's indexed, then it will set that in the confidence tensor, it will set that to this probability corresponding to that index. So basically leave probabilities at their places and set everything else to -infinity. So this will ensure that prompt tokens not masked, so they are not masked, they go to -infinity. Completed blocks already filled, so in the previous blocks they go -infinity. Only masked tokens remain candidates. So even some tokens inside of this block, current block, may not be masked, so they will also go to -infinity. So if we combine this line of code that puts everything after to -infinity, and then with this, then we just have these places where we have these probabilities that we will then pick from. Final result, we only have retained confidence values that are inside the current block and correspond to tokens that are still masked. Then we have this line, so I skip this line in the middle. x0 is equal to torch.where mask index x0 and x. The goal, we are preparing the final prediction tensor x0 that will be partially copied into x, the running output. So this torch where and condition AB. If condition is true at position I, take A of I, otherwise take A of B of I. So our line x of x0 is equal to torch where mask index, take x0, otherwise if false, take x. So where for mask tokens, where mask index is true, use predicted token x0 that we just predicted. For non-masked tokens, keep the original token from x. So keep in mind that when we do this argmax for x0, this picks highest probability tokens for every position, including prompt tokens, which are already known and should not be changed. But x0 does not know which tokens are masked or not. It just predicts for all tokens. So now so wherever the masked token is, we will just, for all of the other positions where there is no mask, we will keep the original x tokens. To get a better understanding of the general idea here, in the first loop, the entire region, entire block, has masked tokens. Mask index is true across the whole block. Model predicts for all these positions. Confidence values are calculated for all, so this is all in the first iteration. Top k highest confidence tokens based on schedule are selected and filled in. The rest remains masked. So yes, first iteration tries to predict the whole block. what happens at later steps in that block. X now has real tokens in some positions. Those we were confident enough to fill in. So mask index is equal to true if X is equal to mask ID. Wait. It seems like this will just give you a list of indices where inside of the X tensor, which is whole batch of everything, tokens are masked. So it will just be true at those places where those masked tokens are. So in these later iterations, it starts keeping some tokens, and more tokens are kept, and more are not masked anymore, and it just iterates like that. So later iterations only refine low confidence tokens. Now let's take a look. Starting from this confidence, we can repeat that and until the end. So the next steps. Goal. Update only a small number of tokens in the current block during the refinement step, the ones we are most confident about. We'll do this by measuring confidence, selecting top K most confident mask positions, replacing just those tokens in X, the original tensor. Confidence. This line says only keep confidence values at mask positions. Everywhere else, set confidence to -infinity. So we just have confidence at mask positions. Result is batch size sequence length. It's filled with false because it's zeros. So it's all filled with false. It will track which positions we want to update in this step. Okay, loop over batch to select top K. Here's what happens per sample J. So in range confidence shape, so for each batch, you get that whole batch, and here is what happens. That batch has shape of just sequence length, the confidence for one sequence, so just a list of array of confidences. And then top K selects the indices of the top K highest confidence values. And it's gonna be, there is a certain number of highest confidences that it selects. So here K is the number of transfer tokens, Ji. So I know that J is the batch, but what is I? I'm not sure. We will see what I is later. So let's see, we selected top K probabilities. Then we have this line X transfer index is equal to X0 transfer index. So we will just pick from X0 the predicted tokens that we want to put into X. So these are the highest probability tokens that we want to now put into X. They are predicted, we will not change them anymore. So only the top K most confident predictions get copied into the main sequence. That's this one. And then we repeat fewer mask tokens, updated X, new model predictions, until the whole block is filled. So basically we have a block, we randomly pick a few, we calculate probabilities for each token over whole vocabulary. We mess up a bit the probability distribution, then pick some tokens, keep the most confident ones, and then repeat. And then only keep the most confident tokens. It's actually quite a simple idea, to be honest. So summary, this first torch where mask index X0 probabilities -infinity. So filter out invalid positions, keep confidence only at masked tokens. And then top K select the most confident masked tokens or tokens at the place where we have these masks, and then transfer them to the X by using this but transfer index Boolean tensor marking where to update tokens in this original final tensor. Now let's explain this I in top K. So we have this matrix number transfer tokens, and it tells us how many tokens to save in each iteration, in each step. So we will just get that number for each batch. So for each batch, for each step, we get how many tokens this step, this iteration we need to transfer to the original X to save. So we get this get num transfer tokens function, and it will return this tensor. So it will take in a block mask index and steps. So if we have 32 mask tokens, for example, and 4 steps, it will assign 8 tokens per step. So it means save 8 tokens each step. If not divisible, then do 9977, for example. So it will pre-compute a schedule. For example, for batch 0, it's 9977 for different steps, and for batch 1, it's 8888.